All right, so in this video, we're going to look at the last topic we need to talk about two sample t-tests, which is calculating two sample t intervals. So confidence intervals around our difference of means. And a lot of the steps are going to be very similar. So we're going to use problems that I've talked about doing hypothesis tests on in other problems. And instead of calculating a hypothesis test, we're going to use that same information to construct a confidence interval on that same data. So some of the calculations are going to be very, very similar. We're going to actually use some of the existing calculations from my other t-test videos. So if you have not yet watched those two sample t-test videos, probably a good idea to watch those along with this one. So we have three situations that we have to think about: the paired test versus the independent situation. And then within the independent case, the pooled versus the unpooled case. Now, if you recall from the test statistics, the paired case turns out to just basically be a one sample confidence interval, which is not that big a deal. It's basically a one sample t-test. And so we have the equivalent of a one sample confidence interval. The pooled and unpooled cases, their complication is that we have to calculate the standard error. Those formulas are more complicated. And particularly for the unpooled case, then we also have another messy formula for calculating the degrees of freedom. So let us go through each of our three previous hypothesis tests and construct the corresponding confidence interval for that same data. So we switch over to the paired data set that we looked at earlier in another video. We have these pairs of training data. Students were selected and matched for having equal IQs. Some of them received some special training to try to improve their test scores, and the other group did not. And then we went ahead and compared them. Now, we have already previously calculated the mean. If we look here, the average of our training data. And actually, we calculated the differences first. That's this. And then we went ahead and we calculated on this difference data the differences for each of the pairs of our students. And then we can use this mean and standard deviation data then and the standard error data to then go ahead and calculate a confidence interval. Now, recall that, and I'll put some of this information over here, the margin of error for our confidence interval is the standard deviation of our sample divided by the square root of n. We have that standard error calculated here. But what we need in order to get the confidence interval is the t critical value, the multiplier. And that's not going to be the test statistic. This is going to have to correspond to the level of our confidence. And that is going to be, we'll just do the 95% confidence interval. We'll use the t dot inverse dot 2t. We're leaving 5% out in the tails if we're leaving 95% confidence in the middle. And then the degrees of freedom is n minus 1. And then our margin of error then is going to be our t value times our standard error. And then the lower bound and the upper bound are going to be the mean minus the margin of error and the mean plus the margin of error. And we know that this agrees with our hypothesis test because our confidence interval contains 0. So notice it flips from a negative value to a positive value within the interval. And that means that we can't tell at our 5% level of significance whether or not these are different from each other. Now, in the original problem, they wanted us to test this at the 5% significance level. If we wanted a 90% confidence interval, of course, we would simply change this t-value. We would leave 10% out in the tails instead of 5% out in the tails. But the fact that this confidence interval contains 0, that is consistent with our inability to distinguish this value from 0. And therefore, since 0 is in the confidence interval, we would also conclude from this that we can't tell that there's a difference, that the training did not seem to make an appreciable impact. And of course, the average is only basically 1 point, so that seems clear. All right, so that's our confidence interval for the paired case. It's basically just calculating the one sample test. We calculate the differences, we do a one sample confidence interval on this data. And because of that, we actually have another way of getting the margin of error. The other way we can get the margin of error is using the function confidence t. The confidence t function is only being applied to a single value. Because in these other cases, they want the standard deviation, and we're not directly calculating the standard deviation or the standard error from that in the same way. So this confidence t function, again, it only produces the margin of error, but we can use it in the paired case because we are essentially doing a one sample test. Our alpha is 0.05. The standard deviation is the standard deviation from our differences, and then the sample size is n. And we can see we got the same margin of error. If we were to try to apply this function, the same confidence t function, to our other scenarios, the pooled and unpooled independent cases, we would not get the same value, which is another indication that we can't use it outside of the paired context. All right, let's go back to another example that we did where we conducted a hypothesis test. This was on the teaching of Ms. Smith and Mr. Jones, and we were trying to determine, based on some test scores, whether or not they were equally effective teachers. And we have some really nasty formulas to deal with. Our test statistic is the difference of the means divided by the standard error. The standard error from this formula is what we need. We calculated it here earlier. This is what we need in order to do our confidence intervals. And then also we need the degrees of freedom that we calculated here to do our t-value, our t-multiplier. So again, watch this hypothesis testing video earlier on in the list to see these individual calculations. But once you have these individual calculations, again, from the summary statistics, we can go ahead and calculate our t-value is going to be, again, t dot inverse dot 2t. Confidence intervals typically are the two-tailed kind. Our probability, if we do a 95% confidence interval, and then the degrees of freedom we calculated was from this crazy formula. And we get our t-value. Again, this is our multiplier. And then the margin of error is going to be our standard error times our t-value. And then the center, this difference of means, is the center of our interval. So I'm going to calculate this explicitly. It's the first group minus the second group. And then our lower bound and our upper bound are that center minus the margin of error and that center plus the margin of error. This is our confidence interval then. This is our, again, this is our unpooled case. Our confidence interval around the difference of means here does not include 0. And that is why we were earlier able to include that this is sufficient evidence that the two teachers are not equally effective, that one of them, Ms. Smith, in this case, is better at her job than Mr. Jones, because it does not contain 0. At the 95% significance level, even at the 95% significance level, this was at confidence level. This was at the 10%, so we could make this a 90% confidence interval if we wanted to be completely identical. Again, it does not contain 0, the confidence interval, and therefore we can conclude there is a difference. And then finally, for the pooled case, again, our pooled standard error down here is in fact what we need for calculating our confidence intervals. And again, we calculated this earlier in the hypothesis test video, and we would just again continue from that same point. Our t-value is going to depend on t dot inverse dot 2t. The probability, again, standard 95% confidence interval. And then the degrees of freedom is essentially this 103. It's N1 plus N2 minus 2. Oh, I have an extra comma in front. And then, and this is a fairly large degree of freedom for this example, which is why we're getting closer to that 1.96 that we get from the z-score. And then the margin is our t-value times our standard error. Again, it's this denominator. It's not the pooled standard deviation. It's not the pooled variance. It's this whole big square root. And then the lower, the difference of means. You have to do that because that's the center of our distribution. 5.2 minus 4.8. And then lower and upper is going to be the difference minus the margin of error and the difference plus the margin of error. And again, similar to our conclusion, we failed to reject the null when we did this as a hypothesis test, and our confidence interval agrees with that. We have a sign flip going on. It's not only negative or only positive. One end is negative, one end is positive. That means 0 is in the middle. And that means we can't tell at this 95% level of confidence if there's any difference from 0 or not. And so if we can't tell the difference from 0, then we can't reject the null. Now, I will say that when you have the data, then you do have, for the pooled standard deviation, there is a shortcut that you can take, and that is that the pooled variance is provided when you use the data analysis toolpack. If you have the data analysis toolpack, you can get this pooled variance to come out of it, and that means that the standard error, you can find that the rest of that formula, but you do have to use this formula. So the pooled variance is this S squared, or sometimes it's written in problems as SP squared. It's this piece. And so in order to get the standard error for the confidence interval, you would still have to do the rest of these calculations using the formula. Same thing for the unpooled case. They've given you some of the information. They've given you your variance S1 squared. They've given you your variance S2 squared. They've given you your sample sizes, but, and they have given you the degrees of freedom, but you are going to have to go back into the problem and you are going to have to calculate. You don't have to calculate the degrees of freedom because that's given to you if you use the data analysis tool pack, but you will still have to piece together using your formulas. You're still going to have to piece this denominator back together in order to get the standard error that you need. So it can circumvent a few things for you, but the data analysis tool pack isn't set up to do confidence intervals. It's set up to do hypothesis testing, and it doesn't input all of the components that you need in order to do the test. Now, if you wanted to be super clever, you may be able, for instance, to take the test statistic and sort of reverse engineer the standard error with a little bit of algebra. But that is shorter, but it does require a little bit of, writing out on a piece of paper. What do you have to do to this test statistic in order to isolate the standard error? And I will leave that as an exercise to the reader.